Hello, today we are going to continue with the study of the Hamilton-Jacobi formalism. Recently we have been doing a lot of examples of how to use the method of separation of variables to solve the Hamilton-Jacobi equation. So now, after finding the solution, we are going to be interested in finding another function s that is going to be the solution for the Hamilton-Jacobi equation, but with a different structure than the first solution that we found. Okay, well, recall that we can establish the Hamilton-Jacobi equation for a given Hamiltonian that has the same structure. It is a function of the qi, the pi, and the time, maybe. Okay, and then for this Hamiltonian, we are able to find a function s that is of the variables qi, pi, t. Well, let me make the difference that this is the little p and this is an upper p. Okay, where this upper p, well, is an element of a canonical transformation that is generated by this s. In fact, if we calculate the total differential of s, we will get that ds is equal to the partial of s with respect to qi dqi plus the partial of s with respect to pi dpi, and then plus the partial of s with respect to time times dt. Okay, and remember that looking that s is a generating function of canonical transformations, we can identify these p's as little pi, and this is upper qi, and this is identified as negative the Hamiltonian. Okay, well, this is like the requirements for s to be a generating function, that minus h is equal to the partial of s with respect to time, upper qi is equal to the partial of s with respect to upper pi, and pi is equal to the partial of s with respect to qi. We have been working with these two equations in the recent examples that we have been watching in other lessons. Okay, so what we are going to be interested in this lesson is to find a new function s tilde that we are going to call that will be a function of the variables qi, upper pi tilde, and the time. Okay, we are going to find a new function that now is going to depend on a new variable pi tilde. So that means that the corresponding equations for this function s are going to be that qi is equal to the partial of s tilde with respect to pi, and upper qi tilde is going to be equal to the partial of s tilde with respect to pi tilde. Okay, perfect. So if we calculate the total differential of s tilde, we will get that this is the s tilde equals to the partial of s tilde with respect to qi, dqi plus the partial of s tilde with respect to pi tilde, dpi tilde plus the partial of s tilde with respect to time, dt, that can be seen as p dqi plus qi tilde dpi tilde minus h dt. So you can see that from this equation that we have here and from this equation that we have here, we can make the subtraction to get that d s minus s tilde is going to be equal to qi dpi minus qi tilde dpi tilde. And we can express this as the differential of a new function f that is going to be the function that is going to represent the canonical transformation that we are interested in, that relates the pi and the qi with the pi tilde and the qi tilde. Okay, this f is telling us what is the relation between these two, well, this transformation. Okay, actually we are going to see that if pi and pi tilde are independent, okay, I mean that pi tilde does not depend on p and p does not depend on pi tilde, well, this means that f is going to be a canonical transformation. Okay, perfect. Another thing we can notice is that for the variable qi, we have that the partial of s tilde with respect to qi is equal to pi, and the partial of s with respect to qi is also equal to pi. We can see this from this expression that we have here, and for this expression here. So that means that the partial of s minus s tilde with respect to qi is equal to 0. And this is telling us that the function that is equal to the difference between s and s tilde, which is f, is going to be independent of the qi. I mean that the expression for f will not contain the qi. So that's why we have the partial derivative with respect to qi equals to 0. Okay, so if we are able to find a function f such that the partial with respect to qi is equal to 0 and has this structure, well, this function is going to be, again, a canonical transformation defined. Okay, so looking that f was defined as s minus s tilde, well, we can set that this new function s tilde is equal to s minus f, where again, looking that this function f does not depend on the qi, we can see that the structure of s tilde is of a function qi pi tilde t. Then s, we know that it has the dependence on qi pi t, and the function f is going to depend only on the pi and the pi tilde. Okay, so we know that the function s tilde depends on qi pi tilde and t. So that means that the partial of s tilde with respect to pi is going to be equal to 0. So that means that the partial of s minus f with respect to pi is equal to 0. So looking that this function s depends on pi and the f depends on pi, well, it turns out that the difference between these two functions do not depend on pi. Okay, so when we make the difference, that pi is going to disappear from the expression, such that the result s tilde is going to be a function that doesn't depend on the pi. Okay, perfect. So we are going to see an example of how to find this function s tilde with a given function f. So recall we have been looking at many examples of the Hamilton-Jacobi equation solution, and one is for the one-dimensional harmonic oscillator. We saw that, well, the function s, that is a solution for the Hamilton-Jacobi equation for the harmonic oscillator, is a function s that depends on q, upper p, and t, given as a minus p squared divided by 2m plus m omega squared q squared divided by 2 tangent omega t divided by omega plus upper pq secant omega t. Again, we made a video where we showed that this is a solution for the Hamilton-Jacobi equation for the harmonic oscillator. So we are going to propose a function that depends on pi and pi tilde, that is going to be of the form p squared divided by 2m omega tangent of p tilde. So with the condition that we have here, that the partial of the difference with respect to pi is equal to 0, we can find a relation between p and p tilde, and then with that relation we are going to erase the dependence of pi in the s tilde. But for now, let's calculate what is s minus f. Well, that is just minus p squared divided by 2m plus m omega squared q squared divided by 2 tangent omega t divided by omega plus pq secant omega t minus p squared divided by 2m omega tangent p tilde. This is upper p, remember. Okay, so we are going to take the derivative with respect to p of all this. So the derivative of s minus f with respect to upper p is equal to, it will be here minus p divided by m tangent omega t, and then plus q secant omega t, and then minus p divided by m omega tangent p tilde. And recall that, well, looking that this is equal to s tilde, the derivative with respect to p of s tilde is equal to 0. So this whole equation is equal to 0. Okay? So if we solve this equation for p, we will get that p is equal to m omega q secant omega t divided by tangent omega t plus tangent p tilde. Okay, perfect. So we know that s tilde is defined to be s minus f, and s minus f is all these things that we have here. So we are going to take this value and we are going to plug it into this equation that we have. So we get that s minus f is equal to minus, it will be, let's say, tangent omega t divided by 2m omega times p squared, but that is m squared omega squared q squared secant squared omega t divided by tangent omega t plus tangent p tilde squared. Perfect. And then minus, it would be m omega q squared divided by 2 tangent omega t for this expression. And then we will have plus q secant omega t times p, but that will make a q squared here, then m omega secant omega t divided by tangent omega t plus tangent p tilde. Okay, and then minus, it will be tangent p tilde divided by 2m omega times p squared, but that is m squared omega squared q squared secant squared omega t divided by tangent omega t plus tangent p tilde squared. Okay, so here we can see that we have a common factor, this and this. So if we take that out, we will get that minus, and let's cancel this m squared with this m and this omega squared with this omega to get m omega q squared secant squared omega t divided by 2 tangent omega t plus tangent p tilde squared, and this is going to multiply tangent omega t plus tangent p tilde, and then minus m omega q squared divided by 2 tangent omega t, and then, well, we have this expression over here, but we are going to multiply on the numerator and the denominator by this element to get this tangent plus tangent squared, and then 2 here and here. So we will get plus 2q squared, let's say m omega q squared secant squared omega t times tangent omega t plus tangent p tilde, and then all these divides 2 times tangent omega t plus tangent p tilde squared. Okay, so with this we can subtract these two elements to get just m omega q squared secant squared omega t tangent omega t plus tangent p tilde divided by 2 tangent omega t plus tangent p tilde squared minus m omega squared divided by 2 tangent omega t. And of course you can see that here we can cancel this element with this squared, so we can rewrite this as this expression. And here we are going to do two things. This we are going to write it as m omega q squared times 1 plus tangent squared omega t using trigonometric identities. Then this divides 2 tangent omega t plus tangent p tilde, and then we are going to multiply here on the numerator and the denominator by this element. So we will get m omega q squared tangent omega t times tangent omega t plus tangent p tilde, and then 2 tangent omega t plus tangent p tilde here. Okay, here we can multiply this element with these two elements here in the brackets to get that we will get tangent squared omega t plus tangent omega t tangent p tilde. Okay, perfect. So here look that we have m omega q squared times tangent squared omega t, and then we are going to subtract m omega q squared tangent squared omega t. So this will cancel with this. So we will get that m omega q squared, then minus, well, it will multiply 1 minus tangent omega t tangent p tilde. So this is divided by 2 times tangent omega t plus tangent p tilde. Perfect. So here is where we are going to remember a very well-known trigonometric identity that says that cotangent of alpha plus beta is equal to cotangent of alpha, cotangent of beta minus 1 divided by cotangent of alpha, cotangent of beta. Sorry, actually this is a sum, right? Cotangent beta. Okay, perfect. But we do not have any cotangent here. So what are we going to do? Well, we are going to multiply by 1 divided by tangent omega t, tangent p tilde, here in the numerator, and then in the denominator we are going to do obviously the same thing to get this. And then what are we going to get? Well, this is going to be m omega q squared times 1 divided by tangent omega t tangent p tilde is of course going to be cotangent omega t cotangent p tilde, and then minus 1, right? So here in the denominator we will get 2 times tangent omega t divided by tangent omega t will be cancelled, and then 1 divided by tangent of p tilde is going to be cotangent of p tilde, and then plus, it will happen the same thing here. We are going to get cotangent of omega t. Okay, perfect. So here's where we use the trigonometric identity to get m omega q squared divided by 2 cotangent of omega t plus p tilde. Okay, perfect. So what we can say about this is that this is a new, different solution for the Hamilton-Jacobi equation for the harmonic oscillator. Okay, we will have a complete different function that is also a solution for this equation, and actually we can see that it is the product of two functions. Yeah, one depends only on q and the other one depends on the t. Okay, so we will think that maybe we are able to find the solution by using the multiplicatively separation of variables method that we talked about on a previous lesson. I remember that we made a video talking about the free particle where we proposed a solution of the form a of q, b of t. Yeah, so what I mean is that this solution is the product of two functions that are only of one variable. So this is like what is happening right now. Maybe if we propose this solution and then plug it into the Hamilton-Jacobi equation, maybe we are going to find this solution here. But recall that actually there are infinite solutions for the Hamilton-Jacobi equation, so I cannot guarantee that will happen. But the thing here is that we were able to find a new solution that is completely different from S for the Hamilton-Jacobi equation. So I hope you enjoyed this lesson, and I think I will finish here.